Welcome to Ask and Learn.
An insulated rigid vessel contains air, and a paddle wheel supplies work to the air. We want to calculate the work supplied and the final temperature. We assume that the air is an ideal gas, the kinetic and potential energy changes are negligible, and the constant specific heats can be used for air. Now we have a constant specific heat, a constant volume of 0.171 BTU per pound mass R. We get this from our table. Now, since the air is a closed system, no mass crosses the boundaries, we can use the energy balance equation that the energy in minus the energy out is equal to delta E for the system, the change in energy of the system. Now, the only energy in here is due to the paddle wheel work. So the work done by the paddle wheel into the system is responsible for a change in internal energy of the system, delta U. And this is equal to mCv delta T, or T2 minus T1. So where m is the mass of air. Now, as the specific volume remains constant during this process, we can use the ideal gas equation and find the final temperature. T2 is equal to T1 times the ratio P2 over P1. And since these values are known, we can calculate the final temperature of the system. So the initial temperature is 520 R, and the pressure in the final state, P2, is 40 psi absolute. The initial pressure of the system is 30 psi. And so we get a final temperature of the system to be 693.3 R, which corresponds to 233.3 Kelvin. Not Kelvin, but 233.3 degrees Fahrenheit. So that's our final temperature of the system. Now we can use this final temperature and substitute it back into our energy balance equation and find the work done by the paddle wheel into the system. Remember, this is m times Cv into T2 minus T1. So this is the mass of air, which is 2 pounds multiplied by the specific heat of 0.171, and that's BTU per pound R, times the change in temperature of 693.3 minus 520 R. And so we get the work done by the paddle wheel into the system to be 59.3 BTU.